Across the North Sea, storm surge forecasting is being pulled toward artificial intelligence, with a new model reading the sea at 4-kilometer resolution, hour by hour, across decades of storm data. On paper, that looks like progress. A system called FLOW is being studied as a graph neural network for storm surge prediction, trained on 43 years of atmospheric and surge data across the North Sea and neighboring waters. But this is not just another technology story. It is happening over a grey, shallow sea that has already shown Europe what a storm surge can do when low pressure, violent wind, high tide, and low land meet in the wrong order. But that is not the most frightening part. The frightening part is not that artificial intelligence is entering the forecast room. It is that even the fastest model still needs the slow, physical truth of the coast. Tide gauges, sea level stations, instruments bolted to harbours, measuring water centimetre by centimetre while the storm is still moving. So the real question is not whether artificial intelligence can make storm surge forecasts faster. The real question is whether the observing network underneath it is strong enough for a higher baseline sea, where small errors turn into hard decisions. Those watching can like, subscribe, and leave a comment with the place they are watching from, because coastal risk is never just a map, it is where people live. The scene begins along a coastline that looks calm only from a distance. On maps, the North Sea appears as a familiar rectangle of cold water pressed between Britain, Norway, Denmark, Germany, the Netherlands, and Belgium. But to forecasters, engineers, port authorities, ferry operators, emergency planners, and people living behind flood walls, it is not just a sea, it is a shallow basin with memory. Along the east coast of England, towns such as Lowestoft, Great Yarmouth, Hull, Grimsby, Immingham, and Whitby face a body of water that can change character when weather systems come down from the North Atlantic. Across the water, the Dutch coast sits behind one of the most complex flood defence systems on Earth. Farther north, Denmark watches low islands, fishing towns, bridges, and energy infrastructure. Germany watches the Wadden Sea, the Elbe, the Weser, and the ports that connect its industrial heart to the world. Norway watches a coastline that is steeper, rockier, and more fragmented, but still tied to the same atmospheric engine. This is the arena into which artificial intelligence is now entering. The event is not a single wave striking a single wall, it is a shift inside the forecast room. A new data-driven model named FLOW is being studied for storm surge prediction across the North Sea, Norwegian Sea, and Barents Sea. It is built as a graph neural network, a type of machine learning model designed to learn relationships across connected points in space. In simple terms, the coastline, the sea, the pressure fields, and the wind fields are not treated as isolated dots. They are treated as a connected pattern. When one part of the atmosphere changes, the model learns how that change may echo through the water. But the people at risk are not living inside a model. They are living in low houses behind embankments. They are working night shifts at container terminals. They are driving coastal roads that may be open at sunset and unsafe before morning. They are maintaining pumping stations, floodgates, seawalls, harbour locks, rail lines, substations, and evacuation routes. They are not waiting for the phrase artificial intelligence. They are waiting for a number. How high will the water get, and when? That is why this story matters. Storm surge forecasting is not an abstract exercise in prediction. It is the difference between closing a barrier too early and disrupting a city, or closing it too late and letting the sea enter. It is the difference between warning a community in time and explaining afterward why the water came higher than expected. It is the difference between a port accepting one more vessel and a port shutting down before cranes, cargo, and fuel storage become exposed. The North Sea is dangerous in a specific way. It is shallow compared with the open ocean, and its shape can help water pile up when strong winds blow across it for long enough. When low atmospheric pressure passes over the sea, the surface can rise slightly beneath it. When gale-force winds push water toward the coast, the rise becomes larger. When that happens near high tide, the danger can multiply. The National Tidal and Sea Level Facility describes a storm surge as a large-scale increase in sea level caused by a storm, with low pressure allowing sea level to rise and strong winds, combined with Earth's rotation, forcing water toward the coastline. For the people on shore, that definition becomes something much less technical. It becomes a harbour gauge, climbing faster than expected. It becomes a police warning not to approach the seafront. It becomes a floodgate crew called in during the night. It becomes a family deciding whether to move a car to higher ground, whether to check on an elderly neighbor, whether to believe that the water will stay outside the door. The official warning chain is built to prevent that moment from becoming chaos. In the United Kingdom, storm surge models are run in real time as part of the Met Office forecasting system. Their results are sent to the Environment Agency and used together with data from the National Tide Gauge Network for coastal flood warning. The current system uses the Nemo Ocean model on the 7-kilometer Atlantic Margin Model domain, known as AMM7, and it runs 4 times per day, producing forecasts up to 2 days ahead. That sounds orderly, and it is, compared with the past, but order does not remove uncertainty, it only manages it. A storm surge warning is never just one number falling from the sky. It is an interpretation of many moving parts. The weather forecast contains uncertainty, the wind direction contains uncertainty, the timing of the peak wind against the timing of the tide contains uncertainty, the local shape of the coast contains uncertainty, the condition of flood defenses contains uncertainty. Even the question of what matters most can change from one harbour to the next. In one place, the critical detail may be the absolute water level. In another, it may be the duration of high water. In another, it may be the waves riding on top of the surge. This is why forecasters do not simply ask whether the sea will rise. They ask how the rise will align with tide, waves, terrain, and infrastructure. The same surge at low tide may be a worrying statistic. The same surge at high tide may be a flood. The same water level at an open beach may be dangerous. The same water level at a defended estuary may become a test of gates, pumps, and human timing. And around the North Sea, the number of systems exposed to that timing is enormous. The ports are among the first to matter. Rotterdam, Antwerp, Hamburg, Bremerhaven, Felixstowe, Immingham, Teesport, and many smaller harbours are not just dots on shipping maps. They are machines made of cranes, roads, rail tracks, warehouses, fuel tanks, customs zones, power cables, drainage systems, and human schedules. When coastal water rises, the impact is not limited to the edge of the quay. It can move into logistics, it can slow cargo, it can close access roads. It can force vessels to wait offshore, it can disturb supply chains that stretch far inland. Then there is energy. The North Sea is one of Europe's major energy spaces. It holds offshore wind farms, subsea cables, gas platforms, service vessels, interconnectors, and coastal substations. Many of these systems are designed for harsh marine conditions, but harsh conditions are not the same as harmless conditions. A storm surge does not need to destroy a wind farm to create stress. It only needs to complicate access, damage a landing point, flood a substation, or force maintenance crews to stand down at the wrong moment. Then there are the communities that rarely appear in technology announcements. A resident in a low-lying street does not experience storm surge as a model grid. A care home near an estuary does not experience it as a probability band. A small fishing business does not experience it as an elegant neural network. They experience it as a warning message, a road closure, a sandbag line, a sleepless night, and the heavy question of whether the sea will stop where the map says it should stop. This is the emotional center of the story. The North Sea's forecasting future is being discussed in terms of artificial intelligence, but the consequences are measured in human exposure. The affected people include port workers, ferry crews, emergency responders, elderly residents, coastal families, farmers behind embankments, rail passengers, power engineers, and public officials who must make decisions before the water arrives. For these people, forecast quality is not a technical luxury, it is the foundation of trust. If a warning is too weak, people may not move. If a warning is too strong too often, people may stop believing the next one. If a barrier is closed unnecessarily, money is lost, traffic is disrupted, and confidence is strained. If it is not closed when it should be, the cost can be counted in flooded homes, damaged infrastructure, and lives placed at risk. Forecasting is therefore not only about prediction, it is about credibility under pressure. This is where artificial intelligence enters with both promise and danger. The promise is speed. A machine learning model can potentially generate results far faster than a full physics-based ocean model. It can learn patterns from decades of simulated and observed behavior. It can operate across a wide area. It can produce a fast picture of how atmospheric pressure and wind may translate into residual water level, meaning the part of the water level caused by weather rather than the normal astronomical tide. But the danger is not that artificial intelligence is fake. The danger is that artificial intelligence can look more complete than it is. A forecast map can be beautifully colored and still be wrong at the point where a road floods. A model can perform well across a region and still miss the local timing that matters to one harbor. A system can be fast and still need confirmation from instruments. A neural network can learn the past and still struggle when the atmosphere produces a rare alignment of wind, pressure, tide, and local geography. The researchers behind Flow are careful about this. They present it as an important step toward complementing traditional physics-based storm surge modeling with machine learning. They do not present it as a replacement that has already solved the problem. Their study says Flow can simulate storm surge water levels at 4-kilometer horizontal resolution and 1-hour temporal resolution, with quality comparable to the numerical model on which it was trained. It also says that because the training hindcast did not include data assimilation, Flow is not expected to systematically outperform the numerical model when evaluated against observations. That sentence is the hinge of the whole story. Data assimilation means the model is regularly corrected with real observations, so the forecast does not drift too far from what the sea is actually doing. Without that correction, a model may be sophisticated, but it is still partly looking at the world through its training history. It can be fast, but it is not omniscient. It can be intelligent, but it is not witnessing the coastline in real time. The witness is the observing network. The United Kingdom National Tide Gauge Network was established after the violent North Sea storms of 1953 produced serious flooding. It records tidal elevations at 42 locations around the United Kingdom coast, and those data are used for flood warning, coastal process research, storm surge behavior, and sea level rise research. That network is the quiet infrastructure beneath the dramatic forecast. It does not announce itself like a breakthrough. It does not look like the future. It looks like metal, cables, sensors, maintenance schedules, calibration work, data feeds, and institutional patience. But when a storm approaches, it becomes the coastal nervous system. The affected coastline depends on that nervous system because the official warnings are not created from models alone. They are created from the interaction between models, observations, forecasters, emergency protocols, and local thresholds. A tide gauge at a harbor does not simply record a number for scientists. It tells the warning chain whether the modeled sea and the real sea are still aligned. If the model says the water should be lower than the gauge says, someone needs to know. If the gauge shows the surge rising faster than expected, someone needs to know. If an instrument fails during a storm, someone needs to know that too, because silence from a sensor can be mistaken for calm if the system is not built carefully. This is why the North Sea should concern people far beyond its beaches. It is a test case for the future of climate risk management. Modern societies are building more and more decisions on model output. Flood defenses, insurance maps, port operations, transport networks, power systems, evacuation plans, and public warnings increasingly depend on forecasts that convert environmental chaos into usable numbers. Artificial intelligence may make that conversion faster, but faster conversion is not the same as stronger truth. The coast still needs eyes. And the North Sea, with its low land, shallow basin, dense infrastructure, deep history, and rising exposure, is a place where this distinction becomes impossible to ignore. The people living around it are not just watching a technological upgrade. They are living inside a warning system that must work before disaster is visible. That is the seriousness of the scene. The sea may appear grey and ordinary. The gauges may sit unnoticed at harbours. The models may run far from public view. The forecasters may work behind screens that most people will never see. But when the wind turns, pressure falls, tide rises, and water begins to lean toward the coast, every quiet part of that system becomes part of the same question. Who will know soon enough? The headline number is small enough to sound precise, and large enough to be dangerous if misunderstood. 4 kilometers. That is the horizontal resolution described for Flow, the data-driven storm surge model being studied across the North Sea, the Norwegian Sea, and the Barents Sea. It is designed to simulate the water level caused by storm surge every hour, across a grid fine enough to make the sea look measurable, structured, almost legible. According to the Flow study, The model is based on a graph neural network and was trained using 43 years of atmospheric and storm surge data, with mean sea level pressure and winds coming from the Norwegian reanalysis system and storm surge information coming from the NORASurge hindcast. 4 kilometers is about 2.5 miles. On land, that can feel small. It is the distance between one side of a coastal town and another. It is the length of a port road, a bridge approach, a ferry terminal zone, a line of warehouses, a stretch of seawall, a few neighborhoods lying behind the same flood defense. It sounds intimate enough to be trusted. But at the coast, 4 kilometers can hide a great deal. It can hide a drainage channel. It can hide the narrow throat of an estuary. It can hide the bend of a harbour wall. It can hide a low road, a sluice gate, a pumping station, a railway embankment, a dune breach, a marina entrance, or a small community sitting behind a defense that looks continuous from the air but is not continuous in weakness. A model cell can be only 4 kilometers wide and still be too wide for the place where water makes its first mistake. That is the first tension in the number. It is a sign of progress, but not a guarantee of safety. For a wide sea, 4-kilometer resolution is impressive. It allows the model to represent broad patterns across a basin that once would have been too expensive to simulate quickly at such detail. It allows the machine to learn how pressure fields, wind stress, and sea level response are connected across many parts of the water at once. A storm system passing over the northern North Sea does not push water in one isolated place. It changes the slope of the sea, the direction of surface stress, and the timing of the surge as it travels. A graph neural network is designed to learn relationships across connected locations, and that is why it is attractive for a sea where one region can become the warning sign for another. But a forecast is not judged only in the middle of the basin. It is judged at the edge. A port manager does not need to know that the model performed well on average across thousands of square kilometers if the quay in front of the port is about to be overtopped. An emergency planner does not need a beautiful regional pattern if the forecast is late by one tide cycle. A barrier operator does not close steel gates because the basin scale image looks elegant. That decision depends on a water level threshold at a particular place, at a particular hour, with little tolerance for false confidence. That is why the second number matters, 1 hour. Flow is described as producing storm surge water levels at 1 hour temporal resolution. On a screen, 1 hour can feel almost real time. It creates a rhythm of prediction that seems close to the rhythm of the storm itself. Every hour, another map. Every hour, another estimate. Every hour, another chance to see whether the water is rising where the model said it would rise. But 1 hour is not always small at the coast. In a storm surge, the height of the water is not the only question. Timing can be just as important. The surge may become dangerous when it overlaps with high tide. If the peak of the weather-driven water arrives earlier or later than expected, the difference can separate a tense night from a flood. A surge that peaks away from high tide may remain below a critical threshold. A similar surge arriving with high tide may push the total water level into a different category of risk. The public often imagines a storm surge as a wall of water arriving all at once, like a breaking wave in a disaster film. But in the North Sea, the more threatening image is slower and larger. The whole surface of the sea can be raised, tilted, and pushed. The danger is not only the peak, it is the alignment. Wind, pressure, tide, and coast have to meet. When they do, the difference between 1 hour and the next may determine whether a floodgate is precautionary or necessary. The National Tidal and Sea Level Facility explains that the current United Kingdom surge model combines the weather-driven surge residual with predicted tides at individual tide gauge sites to estimate total water level. That detail matters because people and infrastructure are not flooded by surge residual alone. They are flooded by the total water level that arrives at the coast. The operational system uses the Nemo Ocean model on the 7-kilometer Atlantic Margin Model Domain, known as AMM7, and it runs 4 times per day, producing forecasts up to 2 days ahead. That comparison gives the flow number its weight. 7 kilometers to 4 kilometers is not a trivial change. It suggests a finer digital sea. 4 runs per day to hourly output suggests a different tempo. A system trained on decades of past atmospheric and surge behavior suggests a machine that can produce estimates quickly, without solving every equation from the beginning each time, in the same way a full numerical model does. But the seduction of those numbers is exactly where the danger begins. A smaller grid does not automatically mean a truer coast. A faster forecast does not automatically mean a wiser warning. A longer training record does not automatically mean that rare events have been understood well enough. 43 years is a large dataset in human terms. In climate and coastal extremes, it is still only a window. It contains many storms, many pressure patterns, many combinations of wind and tide, but it does not contain every possible alignment the future can produce. This is why the phrase "trained on 43 years" should be heard in two ways. It is impressive because it means the model is not guessing from a handful of events. It has been exposed to decades of atmospheric behavior and storm surge response. It can learn recurring relationships. It can learn how the North Sea tends to react when pressure falls, when winds turn, when water is driven southward, when the basin stores and releases energy. But it is also limited because the future is not required to stay inside the training set. A model learns from the world it has seen. A coastline under sea level rise, changing infrastructure, altered storm tracks, modified bathymetry near ports, and shifting exposure may present combinations that look familiar at basin scale, but matter differently at local scale. The past is the teacher. It is not the ocean itself. There is another number hidden behind the headline: more than 90. The FLOW study says the model was evaluated against independent observations from more than 90 water level gauges along the European coast, as well as against the NORA surge hindcast. That is important. It means observations are not an afterthought in the scientific evaluation. They are the reality check. The study found that FLOW produced hindcasts with accuracy similar to the NORA surge hindcast, the numerical model data on which it had been trained. This is both encouraging and sobering. It is encouraging because a machine learning model can reproduce much of the behavior of a physics-based hindcast. That suggests speed, flexibility, and future potential. It suggests that artificial intelligence may become a useful companion to operational storm surge systems, especially where many forecasts, scenarios, or ensembles are needed quickly. But it is sobering because similar is not the same as superior. The FLOW researchers state that because no data assimilation was applied in the NORA surge hindcast used for training, FLOW is not expected to outperform that numerical model when compared with observations. That sentence keeps the story honest. A machine trained on a model can learn the strengths of that model, but it can also inherit its blind spots. If the training world is partly model-made, then the artificial intelligence is not simply learning the sea, it is learning a version of the sea already filtered through another forecasting system. This is the hidden hierarchy behind the headline number. At the top, the viewer sees artificial intelligence. Under it, there is the storm surge hindcast. Under that, atmospheric reanalysis. Under that, numerical physics, historical weather reconstruction, bathymetry, assumptions about wind stress, and comparisons with gauges. And at the bottom, almost always, there is observation, the hard fact of where the water actually was. Without that bottom layer, the upper layers can become beautifully self-referential. That is why 4 kilometers cannot be treated as the final truth. It is a lens, a better lens than many older lenses perhaps, a faster lens perhaps, but still a lens. It must be focused. It must be checked. It must be corrected when the real water disagrees. A 4-kilometer model cell may tell a forecaster that the coast is at risk. A tide gauge tells the forecaster whether the risk is becoming real at a specific harbour. An hourly forecast may show the expected rise. A real-time sensor shows whether that rise is happening faster than expected. A 43-year training record may show what storms have usually done. An observation during the storm shows what this storm is doing now. The headline number, then, should not be read as artificial intelligence has solved the North Sea. It should be read as the North Sea is becoming calculable in new ways, but not fully knowable without instruments in the water. That distinction is not academic. It changes the meaning of trust. When a model becomes faster, there is a temptation to rely on it more. When maps become sharper, there is a temptation to believe they are more certain. When a system uses artificial intelligence, there is a temptation to treat the output as something beyond ordinary error. But storm surge forecasting lives in the margins. It lives in the last centimeters before overtopping. It lives in the hour when a high tide meets a pressure-driven rise. It lives in the places where one side of a seawall stays dry and the other side becomes a floodplain. The number 4 kilometers can impress the mind. The number 1 hour can reassure the schedule. The number 43 years can make the model feel seasoned, almost experienced. But the coast asks a harder question. What happens at the one location where the model is slightly wrong? That is where the story becomes physical again. A harbour does not flood on average. A road does not close regionally. A family does not evacuate statistically. Water crosses thresholds in particular places. It enters through openings. It backs up through drains. It overtops low points. It surrounds substations. It turns underpasses into traps. It follows the geometry that a model may only partly see. So the most important comparison is not between old forecasting and new forecasting. It is between the resolution of the model and the resolution of the real world. The real world has bolts, cracks, valves, curbs, culverts, steps, basements, walls, and doors. The model has cells. The real world has people sleeping through warnings, emergency crews reading dashboards, port operators balancing risk and cost, and forecasters deciding how much uncertainty to communicate. The model has output. The real world has consequences. That does not make the model weak. It makes the model dependent. And dependency is the true meaning of the headline number. 4 kilometers is powerful only if the system around it can tell when 4 kilometers is not enough. 1 hour is useful only if observations can show whether the hour is unfolding as predicted. 43 years of training are valuable only if new data keep the forecast attached to the living sea. The North Sea's artificial intelligence future therefore does not begin with a machine replacing human judgment. It begins with a sharper question for every forecast office, every coastal agency, every port authority, and every government that depends on warning systems. As models become faster and more complex, will the observing network become stronger too? Because the sea does not care how advanced the model is, it rises against the gauge, against the wall, against the door, and against the decision. And when the water comes close enough, the difference between a breakthrough and a warning failure may be measured not in kilometers, but in centimeters. The first mistake is to think the missing key is another algorithm. It is not. The missing key is observation. This is where the story turns away from the clean surface of artificial intelligence and towards something older, heavier, and easier to ignore: instruments at the edge of the sea. Tide gauges fixed to harbours, sea level stations bolted into concrete, pressure sensors sitting in salt water, cables, telemetry, batteries, calibration logs, maintenance crews, quality control checks, and the slow institutional work of keeping a measurement alive through wind, corrosion, funding cycles, and storms. This part of the system rarely appears in a headline. It does not look futuristic. It does not speak in the language of neural networks. It does not promise a revolution. But when a storm surge approaches the North Sea coast, the tide gauge becomes the point where prediction meets reality. A model can say what the water should be doing. A gauge says what the water is doing. That difference is everything. Artificial intelligence can learn patterns from decades of data. It can process pressure fields, wind fields, and previous surge behavior. It can produce forecasts quickly. It can become a powerful new layer in the warning chain. But if the physical observing network beneath it is thin, delayed, damaged, poorly maintained, or spatially incomplete, then the system is not truly seeing the coast. It is estimating the coast. And estimation is not enough when water is within centimeters of a threshold. This is the forgotten truth behind modern forecasting. The future is not made safer by computation alone. It is made safer when computation is anchored to measurement. Without measurement, even a sophisticated model can become a mirror, reflecting its own assumptions. With measurement, the model can be challenged, corrected, reweighted, trusted, or questioned at the right time. That is why the quiet network of tide gauges matters so much. In the United Kingdom, the National Tide Gauge Network exists because history left a scar. It was established after the North Sea storms of 1953, when storm surge flooding exposed how deadly the gap between warning and reality could become. Today, that network records tidal elevations at 42 locations around the coast. Those measurements support coastal flood warning, storm surge research, coastal process studies, and sea level rise monitoring. 42 locations may sound like a lot. Around an entire coastline, it is also a reminder of how much space lies between the eyes. Between one gauge and another, the coast changes shape. An estuary narrows, a harbour turns, a sandbank shifts, a flood wall rises, then dips, a low road cuts inland, a drainage system meets the sea, a river outlet backs up, a town sits behind a defence that may be high enough in one reach and marginal in another. A gauge can report the water level at one site with precision, but it cannot magically report the water level everywhere between sites. This is the central tension. Observations are essential, but observations are never complete. A forecaster must work in the gap between what is measured and what is inferred. Models fill that gap. Artificial intelligence may fill it faster, but the gap remains. And in storm surge forecasting, that gap is not abstract. It can be a neighborhood. It can be an industrial estate. It can be the last low point before water reaches a substation. This is why the story is not artificial intelligence versus old science. That framing is too simple, and it misses the risk. The real story is whether artificial intelligence can be bound tightly enough to the observing network to improve decisions rather than merely accelerate them. The sea is not a spreadsheet. It is a moving surface, shaped by pressure, wind, tide, waves, seabed, coastline, river flow, flood defenses, and human intervention. A barrier closing in one estuary can alter local water behavior. A port modification can change currents. A dredge channel can influence tidal propagation. A storm track shifting slightly south can turn a forecast from manageable to urgent. A high tide arriving at the wrong moment can turn a moderate surge into a flood emergency. No model, physical or artificial, escapes the need to be checked against this moving reality. That checking has a name in forecasting systems: data assimilation. The phrase sounds technical, but the idea is simple. A model starts with its best estimate of the world, then real observations arrive. If the observations show that the world is different from the model's estimate, the model can be adjusted. It can be pulled back toward reality before the error grows. In a storm surge forecast, that may mean using water level observations to correct the modeled sea surface, so the next forecast begins closer to what is actually happening. This is not a minor detail. It is the difference between a model that is only remembering patterns and a model that is also listening. The flow study is careful on this point. It shows that a graph neural network can reproduce storm surge behavior with skill comparable to the numerical hindcast on which it was trained. But it also notes that the training data did not include data assimilation, and therefore the artificial intelligence model should not be expected to outperform the numerical model when compared with real observations. That statement is not a weakness in the research. It is a strength in the honesty. It tells the viewer exactly where the boundary is. Artificial intelligence can learn the modeled sea. The coast still needs the measured sea. That is the distinction that must not be lost. If an artificial intelligence model is trained mostly on the output of a numerical model, then it inherits part of that model's worldview. It learns what that model tends to see well. It may also learn what that model tends to smooth, miss, delay, or underestimate. It can become very good at imitating a simulated history, but imitation is not identical to observation. A forecast system can become fast at repeating an inherited blind spot. That is why the tide gauge is not a relic. It is a form of resistance against self-reference. It interrupts the model with fact. The gauge does not care whether the forecast looked elegant. It does not care whether the map had high resolution. It does not care whether the neural network was advanced. It measures the water against a fixed reference, and if the water is higher than expected, the system has to face it. But even that simple statement hides complexity. Tide gauge data must be reliable. The instrument must be maintained. The reference level must be known. The data stream must arrive quickly. The reading must be quality controlled. The sensor must survive the storm conditions that make it most important. A gauge that fails in calm weather is a technical problem. A gauge that fails during a surge is a blind spot at the worst possible moment. Observation is not just installing equipment. Observation is a long-term promise to keep seeing. This promise is difficult because coastal measurement is physically hostile. Salt corrodes metal, waves damage structures, biofouling affects sensors, power can fail, communications can be interrupted. Harbors are modified, land can subside or uplift. Reference datums must be checked. Instruments need calibration. Data need validation. A sea level record is not just a number in a database. It is the result of years of labor defending accuracy from decay. And yet, this labor is often invisible until something goes wrong. A new artificial intelligence model can attract attention because it seems to belong to the future. A tide gauge network can be treated as background infrastructure because it has already been built, but background infrastructure is where many risks hide. The world tends to notice the dashboard, not the sensor feeding it. It notices the prediction, not the maintenance schedule. It notices the warning, not the uncertainty inside the measurement chain. The North Sea makes that invisibility dangerous. It is not enough to know that a storm surge is forming somewhere offshore. The warning system must know how that surge is evolving as it approaches land. It must know whether the actual water level is tracking the forecast. It must know whether the difference between model and reality is widening. It must know whether a location that looked safe 6 hours earlier is moving toward a threshold. That knowledge comes from observation. Satellites can help. Radar can help. Buoys can help. Coastal cameras can help. Ships can provide reports. Numerical models can fill gaps. But near the coast, where water interacts with walls, channels, estuaries, mudflats, ports, and defenses, direct sea level measurement remains one of the most important anchors. Satellite altimetry is powerful over the open ocean, but the coastal zone is complicated. The closer the problem gets to the flood wall, the more local the truth becomes. That local truth is what a model needs most. The irony is sharp. As forecasting becomes more advanced, it becomes more dependent on ordinary physical measurements. The smarter the system becomes, the more important it is to ask what it is allowed to see. An artificial intelligence model without strong observations is like a skilled navigator with an old chart and a fogged window. It may know the patterns, it may understand the routes, but if the harbour light is out and the water is rising differently than expected, skill alone is not enough. This is why the missing key is not intelligence. It is contact. Contact with the sea, contact with the coast, contact with the actual water height at the actual time when decisions are being made. For a coastal warning system, observation performs several jobs at once. It validates the forecast before the event. It updates the understanding during the event. It improves models after the event. It builds the historical record that allows scientists to study extremes. It tracks sea level rise over decades. It reveals whether rare events are becoming less rare. It gives emergency managers something more concrete than a colored map. And it gives the public something that models alone cannot give: evidence that the warning system is tied to reality. Trust matters because warnings are social events, not just scientific outputs. A forecast must travel from modelers to agencies, from agencies to local officials, from officials to communities, from communities to households, businesses, ports, and vulnerable residents. At each step, the warning can weaken. People ask whether the risk is real. They compare it with previous storms. They decide whether to act. A warning backed by real-time observations can carry a different weight than a warning based only on projection. But the same observation can also create hard choices. Suppose a model predicts a moderate surge, but gauges begin to show water rising above forecast. The warning may need to be escalated quickly. Suppose a gauge reads unusually high, but nearby instruments do not confirm it. Is it a local anomaly, a sensor problem, or an early sign of something the model missed? Suppose communications fail from one station during the storm. Does the system assume normal behavior, or does it treat silence as uncertainty? These are not theoretical questions. They are the operational reality of forecasting under pressure. Artificial intelligence may help detect patterns in those observations. It may flag anomalies. It may combine many data streams faster than a human team can. It may support ensemble forecasting, rapid scenario testing, or local risk translation. But it cannot remove the need for the observations themselves. The algorithm can organize the evidence. It cannot replace the evidence. This is the part that often gets lost in public excitement over technology. The future of storm surge forecasting will not be decided only by the most advanced model. It will be decided by the strength of the entire chain: atmospheric forecast, ocean model, artificial intelligence layer, tide gauge network, data assimilation, forecaster judgment, warning protocol, local preparedness, and public response. Break one link, and the forecast can still look impressive while the system becomes fragile. That is the hidden mechanism behind the North Sea story. The visible story says forecasting is going artificial intelligence. The deeper story says the coast is asking whether the observing network is ready for that responsibility. Because when a storm approaches, a model may produce a forecast every hour, a dashboard may update, a map may change color, a warning center may watch the projected water rise, but outside the screen, the sea continues to move by its own rules. It presses into estuaries, it climbs harbor walls, it surges through channels, it tests drains, gates, and low ground. It turns the abstract into the physical. At that moment, the most important instrument may not be the newest algorithm. It may be a gauge in a harbor, quietly reporting that the water is higher than the model said it would be. The mechanism has a plain name and a complicated personality: storm surge. But that phrase can mislead the public, because it sounds like a wave. It suggests something tall, sudden, and cinematic, a single wall of water breaking over the coast. In the North Sea, the more accurate image is stranger and more unsettling. It is not one wave rising out of nowhere. It is a whole section of sea being lifted, tilted, pushed, delayed, squeezed, and held against the land. The danger begins before the water reaches the shore. It begins in the atmosphere. When a powerful low-pressure system moves over the sea, the air pressing down on the ocean becomes lighter. The ocean surface responds. It rises under the lower pressure. Not dramatically at first, but measurably. This is sometimes called the inverse barometer effect. The name is technical, but the image is simple. The atmosphere is like a hand resting on the water. When that hand lifts slightly, the water underneath can bulge upward. By itself, this pressure effect is usually not enough to create catastrophe. It is one ingredient. The second ingredient is wind. Wind does not merely blow across the surface of the sea. It grips the surface through friction. Over enough distance and enough time, that grip begins to move water. A short gust may roughen the water. A sustained gale can push it. The longer the wind blows in one direction across a large stretch of water, the more the sea surface is forced to lean. Water accumulates where it is being driven. It lowers where it is being pulled away. The sea is no longer level in the way a calm harbor suggests. It becomes a sloping mass. The North Sea is especially sensitive to this because it is shallow. A deep ocean can absorb and spread energy differently. The North Sea, by contrast, sits on a broad continental shelf. Much of it is not deep open ocean, but a relatively shallow basin bordered by low coasts, estuaries, mudflats, ports, and river mouths. When wind pushes water across that basin, the water has limited vertical room and complex horizontal paths. It can be funneled, it can be slowed by the seabed, it can be trapped against coastal geometry. This is why the North Sea is often compared to a long, shallow trough. Imagine a tray of water. If someone blows across it lightly, ripples appear. If someone tilts it, water gathers at one end. If someone keeps pushing from one side while the tray is already tilted, the water does not simply move and vanish. It piles up. Now imagine that the tray is hundreds of kilometers wide, shaped irregularly, connected to the Atlantic at one end, narrowed in places, and lined with cities, ports, barriers, and low land. That is closer to the problem. But wind and pressure still do not complete the mechanism. The third ingredient is tide. The tide is not weather. It is the regular rise and fall of the sea caused mainly by the gravitational pull of the moon and the sun. Because it is predictable, it can feel less dangerous. Tide tables are printed. Harbor schedules depend on them. Coastal life is organized around them. But during a storm surge, the ordinary tide becomes part of the trap. The storm surge is the weather-driven rise. The tide is the astronomical rise. The flood happens when the two arrive together. This is the idea behind tide surge interaction. It means the total water level at the coast is not just the normal tide and not just the surge. It is the combination of both, influenced by timing, coastal shape, seabed depth, friction, and the way water moves through the basin. A moderate surge at low tide may cause concern. The same surge at high tide may cross a defense threshold. A larger surge peaking between tides may look frightening on a graph, but cause less flooding than a smaller surge that arrives exactly when the astronomical tide is already near its peak. This is why timing becomes a form of danger. A storm surge forecast is not only asking how much water will be pushed toward the coast, It is asking when the pushed water will meet the tide. It is asking whether the peak will arrive before, during, or after high water. It is asking whether the water will rise for one tide cycle or stay elevated across several. It is asking whether a flood defense will face one sharp test or a long period of pressure. Duration matters because coastal systems can survive a brief peak and fail under a long one. A seawall overtopped for a few minutes may cause limited flooding. The same wall overtopped for hours may allow enough water to fill streets, overwhelm drains, damage electrical systems, and block emergency access. A pump station can handle a certain rate of inflow. It may not handle sustained backing water. A floodgate can be closed, but if high water lasts too long, the pressure on the protected side of the system changes. Rainwater, river flow, and drainage can become trapped behind defenses meant to keep the sea out. This is why the hidden mechanism is not just height. It is height plus timing plus duration plus local threshold. The National Tidal and Sea Level Facility describes storm surges as large-scale increases in sea level caused by storms, often lasting from several hours to several days and affecting large areas of sea. That scale is important. A storm surge is not a beach event, it is a basin event. It can form far offshore, propagate through the sea, and arrive at different coastlines with different timing and different consequences. The fourth ingredient is Earth's rotation. In the northern hemisphere, moving water is deflected by the Coriolis effect. The name may sound remote from everyday life, but its consequence is practical. As winds and pressure systems drive water through the North Sea, the flow is not a straight push on a flat map. It is bent by planetary rotation. This bending can help pile water toward particular coasts and shape how a surge moves through the basin. The sea is responding not only to the storm above it, but to the rotating Earth underneath it. That is why a storm surge cannot be understood by looking only at the strongest wind on a weather map. The direction of the wind matters. The size of the storm matters. The track of the low pressure system matters. The speed of the storm matters. The shape of the pressure field matters. The stage of the tide matters. The depth of the basin matters. The coastline matters. The seabed matters. The previous state of the sea matters. And because all of these things interact, the outcome can be non-linear. Non-linear means that doubling one ingredient does not simply double the result. A small shift in storm track can change where water piles up. A small shift in timing can decide whether the surge meets high tide. A small change in wind direction can change which coast receives the strongest push. A small error in the estimated water level can matter greatly if the coast is near a threshold. This is why storm surge forecasting is so difficult, and why it is so dangerous to reduce the problem to a single headline number. The public may hear that a surge is 1 meter, but the coast asks where. The public may hear that high tide is near, but the warning system asks when. The public may hear that the model has improved, but the emergency planner asks whether the local gauge agrees. This is where the mechanism becomes operational. A forecast center takes atmospheric information from weather models. Those weather models estimate pressure, wind speed, wind direction, and storm movement. The ocean model, or artificial intelligence system, then translates that atmospheric forcing into a predicted storm surge residual, which is the water level change caused by weather. That residual is then combined with the predicted astronomical tide to estimate total water level at specific coastal sites. In the United Kingdom warning chain, surge model output is used together with tide gauge data because the water that floods land is the total water level, not the residual alone. The distinction matters. A surge residual can be scientifically interesting. Total water level is what reaches a doorstep. If the predicted tide is high and the surge residual is high, the total water level may approach a danger threshold. If waves are also large, the hazard increases further, because waves can run up and over defenses even when the still water level is slightly below the top. If river flow is high at the same time, water trying to drain toward the sea may be blocked or slowed by the elevated coastal water. If heavy rainfall is occurring inland, the drainage system may be stressed from both sides. This is how a coastal flood becomes a compound event. It is not always one hazard acting alone. It can be sea level rise raising the baseline, storm surge raising the weather-driven water, high tide lifting the astronomical water, waves adding impact and overtopping, rain filling rivers and drains. and infrastructure deciding whether the water has somewhere to go. The mechanism is physical, but the disaster is systemic. In the North Sea, the shape of the basin adds another layer. Water entering from the north can be driven southward. Winds can hold water against the coast. The southern North Sea becomes especially important because it narrows and is surrounded by low-lying, densely developed land. Estuaries such as the Thames, the Humber, the Scheldt, the Rhine-Meuse Delta, the Elbe, and the Weser are not just geographic features, they are pathways into infrastructure. An estuary can amplify risk because it connects the sea to the interior. It can funnel water inland. It can place ports and cities at the meeting point between river systems and marine surge. It can force decision-makers to think about both upstream and downstream water. If the sea is high, river water may not drain normally. If river flow is high, the surge may arrive into a system already under pressure. If barriers are closed to stop the sea, water on the landward side must still be managed. This is why a storm surge warning cannot end at the coastline. It has to move into transportation, energy, health, emergency services, ports, communications, and local government. A rising sea level at a tide gauge is not just a marine measurement. It is a signal that road closures may be needed, that rail operators may have to reduce service, that floodgates may need to close, that port cranes may stop, that vulnerable residents may need help, that hospitals and care homes may need contingency plans. The mechanism begins with physics. It ends with decisions. That is why artificial intelligence is attractive. A faster model can help forecasters explore possible futures more quickly. It can support ensembles, where many versions of a forecast are run to show a range of plausible outcomes. It can potentially identify patterns that are difficult to see manually. It can translate atmospheric fields into water level estimates with impressive speed. In a basin where timing is critical, speed has value. But the mechanism also explains why artificial intelligence cannot remove uncertainty by itself. The storm surge depends on the real state of the sea. It depends on the actual wind, not only the predicted wind. It depends on local water levels, not only regional patterns. It depends on whether the surge is already forming differently than expected. It depends on whether the tide gauge network is reporting clean, timely data. It depends on whether forecasters can detect when the model and the water have begun to separate. A model can calculate the mechanism. Observations tell whether the mechanism is actually unfolding. This is the difference between explanation and warning. After a storm, scientists can reconstruct what happened with more data, more time, and more perspective. During a storm, the system must decide while uncertainty is still alive. The pressure field is moving, the wind is changing, the tide is rising, the sea is responding, instruments are reporting, people are waiting, and the forecast is not a historical document. It is a live argument with the future. The most dangerous moment may occur when the model is broadly right but locally wrong. Broadly right means the forecast captures the overall surge. It predicts that water will rise. It identifies the affected coastline. It shows the general timing. Locally wrong means the peak at one harbour is higher than expected, or arrives at a worse hour, or lasts longer, or combines with waves in a way that crosses a threshold. From far away, the forecast looks successful. At the flooded street, the difference is not academic. This is why storm surge science is obsessed with centimetres. To the public, a few centimetres may sound trivial. To a flood defence, they can be the margin between dry and overtopped. To a railway tunnel, they can be the difference between access and closure. To a substation, they can be the difference between exposure and safety. To an evacuation decision, they can be the difference between caution and urgency. Sea level rise makes that margin thinner. If the baseline sea is higher, the same storm surge begins closer to the threshold. The mechanism does not need to become exotic. It can be the same pressure drop, the same wind direction, the same high tide, but acting on a raised platform. What was once a near miss can become an overtopping event. What was once a rare threshold can be reached more often. What was once a modelling error inside the safety margin can become an operational problem. This is the quiet transformation. Climate change does not have to announce itself through a completely new kind of storm for coastal risk to increase. It can work by raising the floor beneath familiar storms. It can make old categories less protective. It can make historical experience less reliable. It can turn the question from whether a storm is unprecedented to whether the infrastructure was built for the baseline from which the storm now begins. That is why the mechanism matters for the whole story. Storm surge is not magic. It is not random punishment from the sea. It is a physical response to pressure, wind, tide, basin shape, rotation, waves, and coast. Because it is physical, it can be modeled. Because it is complex, it can be misjudged. Because it is local at the point of impact, it must be observed. Because sea level is rising, the cost of misjudgment is increasing. The North Sea's artificial intelligence future is therefore not a story about replacing physics with data. It is a story about whether data-driven systems can respect the physics enough to be useful, and whether the observing network can keep those systems tied to the real water. The storm surge does not care whether the forecast came from equations, neural networks, or both. It only responds to the forces acting on it. The warning system, however, must care very much, because every method has limits, and every limit becomes visible at the coast. The image to hold is not a single giant wave. It is a grey basin being pressed from above, pushed from the side, pulled by tide, bent by rotation, slowed by the seabed, narrowed by coastlines, and lifted against places where people have built their lives just above the old line of safety. That is the wall. Not a wall of breaking surf, but a wall made of alignment. Pressure, wind, tide, time, place. When those pieces lock together, the North Sea does not need to roar to become dangerous, it only has to rise. The North Sea has already written this warning once. It did not write it in a research paper. It wrote it across broken dikes, flooded farms, drowned streets, damaged railways, shattered homes, and coastlines that suddenly understood that the sea they thought they knew had another face. The year was 1953, and the lesson was not subtle. A deep, low-pressure system moved across the North Sea. Strong winds pushed water toward low-lying coasts. The surge arrived with the tide. Defences failed. Water went inland. By the time the disaster was fully counted, more than 2,000 people had died across the Netherlands, England, Belgium, and at sea. A later scientific comparison in Frontiers in Marine Science described that surge as the most severe coastal flood in living memory for Northwest Europe. That event is often remembered as history. It should also be remembered as a system test. The flood did not happen because people knew nothing about the sea. Coastal communities had lived with tides for generations. Engineers had built dikes, walls, embankments, and drainage systems. Harbours understood weather. Fishermen understood wind. Officials understood that low land required protection, but the storm exposed a deeper weakness. It showed that knowing the sea in ordinary conditions was not the same as seeing a rare alignment in time. It showed that defences could be strong in normal memory and still weak against the right combination of pressure, wind, tide, and delay. It showed that warning systems, observation networks, and public response were not secondary details. They were the difference between danger and disaster. This is why 1953 still belongs inside a story about artificial intelligence. The modern question sounds different. It involves graph neural networks, hindcasts, atmospheric reanalysis, model resolution, hourly output, and data assimilation. But beneath the new language, the old question remains almost unchanged. Can the system see the water early enough, clearly enough, and locally enough to act before the threshold is crossed? In 1953, the North Sea did not need to produce a mystery, it produced a sequence. A storm system moved, air pressure fell, winds strengthened, water was pushed through a shallow basin, the surge met the tide, the coast was low, defences were overtopped or breached, communications were limited. Warnings did not travel with the speed or clarity that the event required. In some places, people were asleep or unaware when the water arrived. The disaster became catastrophic not because one part failed alone, but because many parts of the coastal system were not prepared for the same extreme at the same moment. That is the pattern modern forecasting is designed to interrupt. After the flood, both Britain and the Netherlands changed the way they thought about coastal risk. The catastrophe led to government reviews, stronger defences, improved flood management policy, and new warning systems. Historical accounts describe how the United Kingdom's response included the development of a storm tide warning service and, later, major protection works such as the Thames Barrier. In the Netherlands, the response became even more visibly architectural. The flood helped drive the construction of the Delta Works, a vast system of dams, sluices, locks, dikes, levees, and storm surge barriers designed to protect the Rhine-Meuse, Scheldt Delta, and other vulnerable areas from the North Sea. The Watersnood Museum describes the delta works as ultimately including storm surge barriers, sluice complexes, and dams built to defend southwest Netherlands from the sea. These structures are often presented as engineering triumphs, and they are, but the deeper lesson is not simply that stronger walls were built. The deeper lesson is that the disaster forced societies to build an entire chain: observation, forecasting, communication, governance, engineering, maintenance, and public trust. A wall without warning can be overtopped without time to respond. A warning without observation can become guesswork. A model without measurement can drift away from the water. That is the bridge from 1953 to the present. The National Tide Gauge Network in the United Kingdom was established after those North Sea storms, and it now records sea level at 42 locations around the coast. Those gauges are not memorials, they are working instruments. Their data support flood warning, storm surge research, coastal process studies, and sea level rise monitoring. In other words, one of the most important consequences of the catastrophe was not only concrete and steel, it was measurement. This matters because memory fades, but instruments keep asking the same question. Where is the water now? That question sounds simple until the storm begins. Then it becomes one of the hardest questions in public safety. The model may predict a peak at a certain hour. The tide table may show when astronomical high water should occur. The pressure chart may show the passing low. The wind forecast may show the push across the basin. But the gauge says whether the water at the coast is following the expected path. It brings the system out of theory and into contact. The tragedy of 1953 was not only the height of the water, it was the absence of a modern, integrated warning system capable of translating the developing surge into timely action across many exposed communities. The modern danger is different, but not unrelated. Today, the warning system has far more tools. It has numerical models, it has weather satellites, it has tide gauges, it has communications networks, it has emergency protocols, and now, it may increasingly have artificial intelligence. But the existence of tools does not automatically create safety. The flood of 1953 proves that coastal risk is a chain problem. If one link is weak, the whole system can fail at the moment of stress. In the past, weak links included limited forecasting, limited monitoring, limited warning communication, and defenses designed around an incomplete understanding of extremes. In the present, the weak link could be more subtle. It could be overconfidence in model output. It could be underinvestment in sensors. It could be a data gap near a vulnerable estuary. It could be a communications failure during the storm. It could be a warning that arrives technically correct but socially ineffective. The past does not repeat as a copy. It repeats as a structure. That structure appeared again in a different form when later North Sea surges tested upgraded defenses. One important scientific comparison examined the 1953 surge alongside the surge caused by Storm Xaver in 2013. The study noted that the later event produced very high sea levels in parts of the North Sea, yet caused far less loss of life and damage in the United Kingdom than 1953, partly because forecasting, warning, and flood defenses had improved. That comparison is crucial. It shows that society is not helpless. Better forecasting matters. Better defenses matter, better warnings matter, institutional memory matters. The same sea, the same kind of physics, and the same broad basin can produce a very different human outcome when the system is prepared. This prevents the story from becoming fatalistic. The North Sea is dangerous, but danger is not destiny. However, the comparison also carries a warning. If lower damage in a later event is interpreted as proof that the problem has been solved, then success becomes a new risk. A defended coast can become complacent. A population behind barriers can forget that barriers are active systems, not permanent promises. A government can fund visible upgrades while quietly neglecting monitoring. A public can remember that the last warning did not become a catastrophe and assume the next one will not either. This is how historical memory can decay into false security. The sea does not care that a society improved after the last disaster. It tests the system that exists when the next surge arrives. That is why the history has to be read carefully. 1953 does not say that every North Sea storm surge will become a catastrophe. It does not say that artificial intelligence forecasting is dangerous by itself. It does not say that defenses are useless. It says something more precise and more disturbing. Coastal disaster emerges when physical extremes meet weak system links. A surge is the physical trigger. The disaster is the chain reaction. This is the same logic that should guide the evaluation of artificial intelligence forecasting. A graph neural network can be a valuable link. It can run fast. It can learn basin-scale relationships. It can support forecast ensembles and scenario analysis. It can help agencies see possible surge evolution earlier or more frequently. But if that link is added to a chain whose observing network is undermaintained, sparse, delayed, or poorly integrated into decision-making, then the chain has not necessarily become strong. It may only have become more complex. The history of the North Sea argues against both panic and hype. Panic says the sea is unknowable and nothing can be done. That is false. Decades of improved forecasting and defense show that science and engineering save lives. Hype says the newest model will solve the problem. That is also false. 1953 shows that the problem is never one model alone. It is the entire path from atmospheric warning to sea level measurement to flood defense operation to public action. This is why the tide gauge is the historical object that matters most in the artificial intelligence story. It is not glamorous. It is not new. It is not a symbol of technological acceleration, but it represents the lesson learned in water. After a catastrophic surge, societies did not only build higher defenses, they built ways to watch the sea. They accepted that the coast had to be measured continuously, not remembered occasionally. That lesson becomes more important, not less, in an artificial intelligence era. The more advanced the model becomes, the more damaging it can be if the system forgets what the model is attached to. If artificial intelligence is trained on a hindcast, it has learned from a reconstruction of past water levels. If it is evaluated against gauges, it still needs those gauges to judge whether it has remained honest. If it is deployed in warning support, it will need current observations to know whether the present storm is behaving like the learned pattern or slipping outside it. The history also shows why rare events are so difficult. A storm surge disaster may sit outside the daily imagination of a coast for decades. People build, invest, commute, retire, and raise families in places that feel safe because they have not flooded recently. Defenses become part of the scenery. Warning systems become invisible. Emergency plans become documents. Then an extreme event compresses decades of neglected assumptions into a few hours. That compression is what 1953 revealed. It revealed that the coast is not protected by the absence of recent disaster. It is protected by the quality of preparation during quiet years. Artificial intelligence enters during a quiet year, not during the flood itself. That is the moment when choices are made, whether to fund more gauges, whether to maintain old stations, whether to integrate observations into models, whether to preserve human expertise, whether to explain uncertainty honestly, whether to test warning chains before the storm, whether to treat artificial intelligence as a support tool inside a larger system, or as a shiny surface that hides older vulnerabilities. The North Sea's past is not asking modern forecasters to reject new technology. It is asking them to remember why the technology exists. It exists because water once came higher than systems were ready to handle. It exists because people died not only from physics, but from unreadiness. It exists because observation, warning, and response had to become faster than the surge. It exists because a coastline cannot afford to learn the same lesson only after the water has already entered. The precedent is therefore not a museum piece. It is a diagnostic tool. When a new artificial intelligence model appears, the historical question should not be, is this impressive? It should be, where does it strengthen the chain? Does it help forecasters see the surge earlier? Does it expose uncertainty more clearly? Does it work with tide gauges rather than float above them? Does it improve decisions at the coast, or only improve the appearance of prediction on a screen? 1953 answers in silence. It points to the places where water crossed defenses. It points to the gap between warning and arrival. It points to the need for measurement. It points to the long memory built into gauges, barriers, and forecasting services. And it warns that every generation inherits not only the defenses built after disaster, but also the temptation to believe those defenses have ended the danger. They have not ended it. They have changed its terms. The North Sea today is watched more closely than it was then. It is modelled more deeply. It is defended more strongly. It is connected to faster communications and more advanced science. But it is also bordered by denser infrastructure, larger ports, higher expectations of continuity, and a rising baseline sea. The next failure may not look like the last one. It may not come from ignorance. It may come from a small mismatch between confidence and reality. That is why the old disaster remains new. It reminds the system that the sea does not need society to forget everything. It only needs society to forget one essential thing. Prediction is not protection unless it is tied to observation, tested by history, and translated into action before the water arrives. The most fragile part of a storm surge is not always the seawall. Sometimes it is the road behind it. Sometimes it is the substation beside the road. Sometimes it is the drainage outfall that cannot empty because the sea outside is too high. Sometimes it is the port access gate, the tunnel entrance, the railway signal cabinet, the fuel terminal, the care home, the ferry ramp, the warehouse floor, the pumping station, or the single low place where a defended coastline is not as continuous as it looks on a map. This is the layer that makes the North Sea story heavier than a forecast model. The water level is the headline, the vulnerability is the plot. A storm surge becomes a disaster when it finds a threshold. That threshold may be physical, like the crest of a flood wall. It may be electrical, like the height of a cable entry point. It may be operational, like the water level at which a port shuts down. It may be social, like the moment when people can no longer evacuate safely. It may be institutional, like the point where emergency services have too many simultaneous calls and not enough routes. This is why a forecast error of a few centimeters can matter more than it sounds. The public often imagines coastal flooding as a simple contest between water and land. If the water is higher, the land floods. If the water is lower, it does not. But real infrastructure does not fail as a smooth line. It fails in steps. A few centimeters may do nothing for hours, and then suddenly reach the underside of a door, the lip of a quay, the opening of a tunnel, the edge of a switch room, the low point of a road, or the overflow height of a drainage system. Below the threshold, the system looks normal. Above it, consequences begin to spread. This is the danger hidden beneath the headline number. A storm surge forecast may say the peak water level will remain just below a critical mark. That sounds manageable. But if sea level observations show the water tracking higher than expected, or if the wind holds longer, or if waves run up over the defense, or if heavy rain is filling the land side of the drainage system at the same time, the margin can disappear. The event does not need to become spectacular everywhere. It only needs to cross the wrong threshold somewhere important. The North Sea has many such places. It has ports that are not only maritime facilities, but economic organs. Rotterdam, Antwerp, Hamburg, Bremerhaven, Felixstowe, Immingham, and many smaller ports connect inland factories, fuel systems, farms, chemical plants, warehouses, supermarkets, construction sites, and energy networks. A port is not just a line of cranes beside water. It is a dense arrangement of roads, rails, pipes, power supply, control systems, berths, gates, terminals, customs areas, workers, and schedules. When water rises into that arrangement, the effect can move faster than the flood itself. The Port of Rotterdam openly treats climate adaptation as a working problem, including flood risk management, sea level rise, wind, rainfall, saltwater intrusion, and the need for a resilient chain for the chemical sector. That matters because Rotterdam is not merely a coastal landmark. It is one of Europe's great logistical engines, and flood risk there is also a question of continuity for industries far beyond the harbour fence. The word continuity is important. Modern infrastructure is built around continuity. Electricity should stay on, fuel should move, food should arrive, ports should reopen, roads should drain, emergency services should reach people, communications should not fail, rail systems should restart, insurance systems should process claims, hospitals should function. A storm surge attacks continuity not only by destroying things, but by interrupting the systems that make daily life seem stable. This is why the vulnerable layer is so broad. First, there are the obvious communities, low-lying coastal towns, villages behind embankments, neighborhoods near estuaries, houses built close to tidal rivers, farms in reclaimed land, and islands where escape routes may be limited. These communities know the sea is nearby, but knowing does not make them equal. A wealthy household can raise utilities, insure property, move vehicles, pay for repairs, and leave early. A poorer household may not have a car, savings, flexible work, or a safe place to go. A warning does not land on everyone with the same force. Then there are elderly residents, people with disabilities, care home residents, hospital patients, people who rely on powered medical equipment, migrants with weaker access to official warnings, and workers whose jobs require them to remain near the hazard. For these groups, the question is not only whether a warning is issued, it is whether the warning is understandable, trusted, accessible, and early enough to matter. A model forecast cannot solve that alone. It can say water may rise. It cannot make sure a person in a ground floor flat receives help. It cannot clear a blocked road. It cannot move a wheelchair user upstairs. It cannot restore power to a flooded substation. It cannot reopen a rail line if signal equipment has been damaged by saltwater. It cannot make a community trust an evacuation order if previous warnings were confusing or exaggerated. This is where coastal risk becomes social. The second vulnerable layer is transport. Coastal roads often run where land is flat, where communities grew, where ports developed, and where river mouths meet the sea. Rail lines in many coastal regions follow low corridors because those corridors were historically practical. They connect ports to cities, workers to jobs, and freight to inland distribution. But low corridors are also exposed corridors. A United Kingdom transport hazard summary warns that coastal flooding and erosion are a growing risk to roads, railways, and ports near the coast, with the potential for 1 meter or more of sea level rise before the end of the century, making more low-lying routes exposed to seawater more often. Transport is especially vulnerable because it depends on networks, not isolated objects. A flooded section of road can isolate a dry neighborhood. A closed rail segment can disrupt an entire line. A damaged bridge approach can cut access to a port. A tunnel entrance can become unusable, even if the tunnel itself is structurally sound. Saltwater can corrode equipment long after the visible flood has gone. Sediment and debris can block drainage. The surge may last hours, but the repair can last weeks. The third vulnerable layer is power. Electricity systems dislike water, especially salt water. Coastal substations, cable landings, control cabinets, pumping stations, distribution nodes, and backup generators may be protected by walls, elevation, seals, and operational protocols. But the risk is not only direct inundation. Access matters, cooling systems matter, communications matter. Workers must be able to reach equipment safely, replacement parts must arrive. The system must keep operating while other parts of the coast are also under stress. The North Sea adds a special twist because it is becoming central to Europe's energy transition. Offshore wind farms, subsea power cables, interconnectors, offshore platforms, and coastal grid connection points turn the sea into both a hazard zone and an energy corridor. The same basin that can push water toward vulnerable coasts also carries critical infrastructure for a low-carbon future. A storm surge does not have to topple turbines to create trouble. It can flood landfall sites, delay maintenance vessels, stress port operations, and complicate grid management during a wider storm. This is a systemic risk because infrastructure systems depend on each other. A flood at a substation can affect pumps. Failed pumps can worsen flooding. Flooded roads can prevent repair crews from reaching the substation. Lost power can affect communications. Weak communications can slow emergency coordination. Port closures can delay fuel or replacement equipment. A hospital may be dry, but if roads, power, staff movement, and supply chains are disrupted, the hospital is still affected. The storm surge is the trigger. Interdependence is the amplifier. This is why coastal infrastructure risk assessments increasingly treat flooding as more than a line on a map. The United Kingdom Climate Risk Assessment chapter on infrastructure notes that coastal infrastructure is particularly at risk from storm surges, rising sea levels, and coastal erosion. It also emphasizes that infrastructure networks are interdependent, meaning failure in one system can cascade into others. That word cascade should stay in the mind. A cascade is what happens when one failure creates the conditions for another. The water does not have to enter every building, it only has to touch the wrong node. It only has to close the wrong access route. It only has to disable the pump needed to protect the next district. It only has to make a port unavailable when emergency logistics require it. It only has to make a forecast look slightly too calm until action is late. This is where observations return to the center of the story. If the forecast says a surge will stay below a port threshold, but gauges show the water rising faster than expected, the port may need to change operations. If the forecast says a high water window will be short, but observations show the elevated water lasting longer, drainage managers may face a different problem. If one tide gauge confirms the model and another nearby gauge does not, forecasters must decide whether the difference is local physics, instrument error, or the first sign of a missed pattern. Infrastructure is not protected by average accuracy. It is protected by knowing when the local situation is different. Artificial intelligence can help identify patterns across large areas, but local vulnerability is often brutally specific. One station platform may be slightly lower than another. One road underpass may flood before the main carriageway. One industrial site may have raised its critical equipment, while another has not. One neighborhood may have strong community warning networks, while another may depend entirely on official messages. One flood barrier may have redundancy, while another requires crews to arrive physically at the right time. The difference between resilience and failure is often hidden in details too small for a regional model cell. This does not mean models are useless. It means models must be connected to local intelligence. A storm surge forecast can show where pressure is building across the basin. Tide gauges can show whether water levels are matching expectations. Local flood maps can show where overtopping may matter. Infrastructure operators can show which thresholds matter for their systems. Emergency planners can show who needs help first. The warning becomes strongest when these layers talk to each other. The weakest warning is a beautiful forecast, sitting alone. The strongest warning is a forecast checked by observations, interpreted by experts, translated into thresholds, and acted on by institutions that have practiced what to do. The communities around the North Sea are not equally ready for that process. Some live behind world-famous defences. Some live behind older walls and embankments. Some live in places where protection is being upgraded. Some live in places where managed realignment, erosion, or long-term adaptation will become unavoidable. Some depend on local councils with limited budgets. Some depend on national systems. Some may not know whether the defense in front of them is designed for the risk that is now arriving. That uncertainty has an emotional weight. A person behind a flood wall may feel safe because the wall is visible, but the real protection may depend on a forecast center far away, a tide gauge reporting clean data, a barrier operator making a decision, a pump running, a power supply holding, a road staying open, and a warning message reaching the right people in time. The wall is the part they can see. The system is the part they must trust. And trust is difficult when the system becomes more technical. Artificial intelligence may improve forecasting, but it may also make the warning chain feel more opaque to the public. If an official says a traditional model predicts a certain water level, the public may not understand the equations, but the idea of a physical model is familiar. If an official says an artificial intelligence system has adjusted the risk estimate, people may ask what it saw, what data it used, and whether anyone can explain the uncertainty. Transparency becomes part of resilience. The vulnerable layer therefore includes not only concrete and cables, but communication. A warning that cannot be explained may be ignored. A warning that sounds too certain may damage trust if the event misses. A warning that sounds too uncertain may fail to trigger action. A forecast system that uses artificial intelligence must still give human decision-makers a way to understand why risk is rising, where confidence is strong, where uncertainty is large, and what observations are confirming or contradicting the model. This is why the North Sea's transition toward artificial intelligence forecasting cannot be judged only by model skill scores. The deeper measure is whether the system improves decisions for the places most likely to suffer. Does it help a port close at the right time? Does it help a flood agency issue a clearer warning? Does it help identify an estuary where the surge is arriving higher than expected? Does it help emergency planners prioritize communities with limited mobility? Does it help operators understand when a substation or pumping station is approaching a threshold? Does it give enough lead time without hiding uncertainty? If the answer is yes, artificial intelligence becomes part of resilience? If the answer is no, artificial intelligence becomes another layer of confidence over old vulnerability. The harsh truth is that storm surge risk is not distributed evenly. Some places have stronger defenses, better monitoring, richer institutions, and clearer emergency protocols. Others have aging infrastructure, weaker budgets, fragmented responsibility, and communities already under stress from housing costs, health inequalities, or declining local services. When the sea rises, it does not create those inequalities. It reveals them. That is why the event is more dangerous than the headline number. The headline number says the water may rise by a certain amount. The real risk asks who lives where that amount matters, which road closes first, which pump fails, which warning is missed, which port threshold is crossed, which worker is still on site, which elderly resident cannot leave without help, which emergency route becomes unavailable, which decision-maker receives data too late. Storm surge is a physical event. Disaster is a social and infrastructural event built on top of it. The North Sea's future forecasting system must therefore see more than the sea. It must see the coast as a living network of dependencies. It must see that a centimetre at a gauge may be a decision at a barrier. A delayed observation may be a delayed warning. A flooded road may be a failed rescue. A port closure may be a supply chain shock. A substation flood may become a neighbourhood without power. A confusing alert may become public hesitation. This is the missing human layer in a story that could otherwise become too technical. Artificial intelligence can make the forecast faster. Observations can make it honest, but vulnerability decides what the forecast means. And around the North Sea, vulnerability is not only sitting at the edge of the water, it is threaded through the ports, the dikes, the grids, the roads, the homes, the farms, the care facilities, the industrial zones, and the quiet assumptions that tomorrow's coast will behave like yesterday's. That assumption is becoming harder to defend. The deeper story is not that the North Sea is getting a new kind of forecast. The deeper story is that the baseline beneath every forecast is moving. That is the change that makes this moment larger than artificial intelligence. A storm surge has always been dangerous when pressure falls, winds push water, and the tide is high. But sea level rise changes the starting point. It lifts the floor under the entire event. It means the same surge can begin from a higher sea, reach a flood threshold faster, and turn a margin that once looked safe into a margin that no longer exists. This is not the same as saying every storm is becoming stronger. That would be too simple. The more precise statement is more unsettling. Sea level rise does not need to make every North Sea storm more violent in order to make coastal flooding more likely. It only has to raise the water on which those storms act. A familiar storm moving over a higher baseline sea can produce a new outcome at the coast. The storm may look meteorologically ordinary, the damage may not. This is the new baseline. It is not a future where every tide looks dramatic. It is a future where ordinary high tides sit closer to flood thresholds, where storm surge residuals have less empty space to rise through, where waves begin from a higher platform, and where small forecast errors become less absorbable. The European Environment Agency states that increases in mean local sea level are the main driver of observed and projected increases in extreme sea levels along European coastlines. It also warns that coastal floods are a growing threat to buildings, energy and transport infrastructure, water supplies, and human lives. That is the mechanism by which centimetres become policy. A centimetre sounds small on a ruler. At the coast, it can be a lost safety margin. Several centimetres can change how often a road floods. Several more can change whether a storm tide overtops a quay. Over decades, the rise becomes embedded in every warning, every flood map, every barrier operation, every insurance model, every harbour plan, and every argument over whether to defend, adapt, or retreat. The storm surge forecast still asks, how high will the water get? The climate question asks, high compared with what? That second question is the one that many systems were not built to answer. Much coastal infrastructure was designed around historical ranges. The seawalls, drainage outlets, roads, power systems, port thresholds, and emergency plans often carry an assumption about what counts as rare. A once-in-a-century water level was not meant to become a routine planning problem, but the European Environment Agency projects that, because of relative sea level rise by the end of the century. Historical once-in-a-100-year coastal floods could occur at least once a year along most European coasts under a high emissions scenario, and at least once a decade along remaining European coasts, even under lower emissions scenarios, except in parts of the northern Baltic, where land uplift changes the picture. This does not mean every coastline will experience the same outcome. Local land movement matters. Coastal defences matter. Sediment matters. Estuary shape matters. Storm tracks matter. Governance matters. Wealth matters. Maintenance matters. But the direction of the pressure is clear. The old statistical language is being pulled out of alignment with the new physical reality. A rare event can become less rare without changing its name. That is one of the most dangerous features of climate risk. The vocabulary stays stable while the meaning shifts underneath it. A flood defense designed for a historical standard may still be called protective. A warning threshold may still be called critical. A port may still describe an event as exceptional. But if the baseline sea rises, the number of times the system is tested can increase. The label may remain the same. The stress does not. This is where the North Sea becomes a system story. The region is not only exposed because it has low coasts, it is exposed because it is intensely connected. Ports feed supply chains, offshore wind feeds power systems, subsea cables connect grids and data. Industrial zones depend on stable logistics. Rail and road corridors carry workers and goods. Flood barriers protect cities, but they also require decisions, maintenance, authority, and timing. A surge does not strike an empty coast, it strikes a network. That network is already operating under pressure from many directions. Climate change adds sea level rise. Economic systems add demand for continuity. Energy transition adds more offshore infrastructure. Urban growth adds more people and assets in low-lying zones. Aging infrastructure adds maintenance burdens. Public budgets add political limits. Emergency agencies add staffing constraints. Forecast systems add more data, more models, and more uncertainty to interpret. The result is not just higher water. The result is decision overload. A faster artificial intelligence model can produce more forecasts, more scenarios, more updates, more spatial detail, and perhaps more warning lead time. That sounds useful, and often it is. But more information does not automatically become better action. Someone still has to decide what the information means. Someone has to compare it with observations. Someone has to judge whether the signal is strong enough to close a barrier, evacuate a neighborhood, halt port operations, suspend trains, move equipment, activate pumps, or issue a public warning that will carry economic and social cost. If the system receives more model output but not enough reliable observations, the bottleneck shifts. The bottleneck is no longer raw calculation. It becomes verification. It becomes interpretation. It becomes trust. The Copernicus Climate Change Service describes its European storm surge work as providing climate data on storminess, tide, waves, and sea level rise to support long-term decisions for coastal sectors, including flood control barriers, offshore wind operations, port accessibility, coastal zone management, and flood risk from surge and wave overtopping. That list matters because it shows storm surge information is no longer only a meteorological product. It is becoming a planning tool for whole sectors. But planning tools can fail if the data chain is weak. A port planning for future access needs to know not only the average sea level rise, but how often thresholds will be crossed during storms. An offshore wind operator needs to know not only wind speed, but vessel access windows, wave conditions, water levels, cable landfall exposure, and port availability. A flood barrier operator needs to know not only that a surge is possible, but whether the latest gauges show the water departing from the forecast. A city needs to know not only the map of hazard, but the map of people who cannot move quickly. This is why observations become more important as the climate changes. A stable world can tolerate older assumptions for longer. A shifting world punishes stale assumptions. Tide gauges do not merely support a forecast during one storm, they track the baseline as it moves. They show whether local relative sea level is rising faster or slower than the global average. They reveal whether subsidence is adding hidden risk. They preserve the long record that allows scientists to distinguish noise from trend, unusual tide from new normal, and model bias from real change. Without that record, adaptation becomes guesswork with expensive consequences. Build too little, and the water exposes the error. Build blindly, and money may be spent in the wrong place. Warn too late, and people suffer. Warn too often without explanation, and public trust erodes. The new baseline therefore demands a new kind of humility. It requires a warning system that can say not only what the model predicts, but how the prediction is being checked. It requires agencies to know when the artificial intelligence is confident because the physics and observations agree, and when it is confident only because it has seen a similar pattern in training data. It requires decision makers to recognize that a model can be skillful on average and still leave a dangerous local uncertainty at the edge of a port, estuary, or defended town. This is the hidden challenge of climate adaptation. It is not simply building higher walls. It is keeping the whole system honest while the boundary conditions change. The Intergovernmental Panel on Climate Change emphasizes that cities and settlements by the sea face interacting risks and adaptation limits, and that combinations of protection, accommodation, nature-based measures, and in some cases, retreat may be needed as sea level rise continues. That is a careful scientific way of saying the old single answer is breaking down. Defend everywhere forever is not always possible. Retreat everywhere immediately is not socially or politically simple. The future is a contested space between engineering, economics, geography, justice, and time. The North Sea shows that contested space clearly. The Netherlands has world-famous defences, but also vast assets behind them. Britain has exposed estuaries, aging coastal towns, and major ports. Germany has the Wadden Sea, tidal rivers, and industrial corridors. Denmark has low islands and coastal settlements. Norway has a different coastal shape, but remains connected to the same regional storm systems and marine operations. Each country sees a different coast. The atmosphere sees one basin. That is why storm surge forecasting cannot be treated as a national problem only. Water does not stop at political boundaries. Pressure systems cross forecast domains. Surge signals move through connected seas. Shipping schedules, energy infrastructure, and supply chains span countries. A warning weakness in one part of the basin can matter elsewhere. An offshore asset may depend on one country's port, another country's grid connection, and a forecast produced by a third institution. Artificial intelligence may make cross-border forecasting more powerful. It may also make dependency more opaque. If several agencies begin using related datasets, related hindcasts, or related machine learning approaches, they may share not only strengths, but blind spots. A bias in training data can travel quietly through products. A sparse observing region can remain sparse beneath multiple sophisticated outputs. A missing gauge can be hidden by the smoothness of a model field. A flawed assumption about the baseline can propagate into infrastructure plans that look independent, but were built on similar information. This is why the phrase missing key matters. The missing key is not that the North Sea lacks models. The missing key is that models, especially artificial intelligence models, must be continuously confronted by the coast itself. That confrontation has to happen before, during, and after events. Before an event, long-term observations define the baseline and reveal trends. During an event, real-time observations confirm whether the forecast is tracking reality. After an event, observations show where the model performed well, where it failed, and which local thresholds mattered most. Each stage feeds the next. Without that cycle, the system may become faster, but not wiser. A new baseline C also changes the meaning of false alarms. In the past, a warning that did not lead to flooding might be dismissed as overcaution. In a changing climate, some near misses are useful information. They show how close the water came. They reveal which defenses were nearly tested. They show whether public response worked. They expose where communication failed. They can help recalibrate thresholds before the next event. But that learning only happens if observations are good enough to reconstruct the near miss in detail. A near miss without measurement becomes a story. A near miss with measurement becomes evidence. The same is true for small floods. A few flooded roads, a delayed ferry, a closed rail segment, or a port operation suspended for several hours may not become international news. But such events can reveal the new baseline earlier than catastrophes do. They show that the system is being touched more often. They show where disruption begins. They show whether adaptation is keeping pace with the water. That is why the future may arrive quietly. Not first as a once-in-history disaster, but as more frequent edge events, more nuisance flooding, more threshold crossings, more warnings, more barrier operations, more drainage conflicts, more days when ports operate under constraints, more insurance questions, more maintenance after saltwater exposure, more arguments about whether to hold the line or move back. The North Sea will still have dramatic storms, but the larger transformation may be statistical and operational. A world with a higher baseline sea is a world where the same infrastructure is asked to perform more often near its limits. Forecast systems are asked to issue more nuanced warnings. Emergency managers are asked to prepare for events that are no longer rare enough to ignore, but not always extreme enough to mobilize the whole state. Communities are asked to live with risk that is neither constant disaster nor comfortable safety. That middle zone is psychologically difficult. People understand catastrophe. They understand calm. They struggle with creeping risk. They struggle with a shoreline that looks the same but behaves differently. They struggle with the idea that a few centimeters can matter. They struggle with warnings that say the event may be serious if timing shifts by 1 hour. They struggle with uncertainty that is honest but hard to act on. This is why the future of storm surge forecasting is partly a communication problem. Artificial intelligence can create better tools, but agencies must still explain what those tools mean. They must explain that a forecast is not a prophecy. They must explain that uncertainty is not ignorance. They must explain why observations matter. They must explain why a tide gauge reading can change a warning. They must explain why sea level rise makes old benchmarks less reliable. They must explain why a storm that looks ordinary on a weather app may be dangerous at the coast. The system must become not only smarter, but more legible. Because if the public cannot understand why warnings change, trust may fail at the wrong moment. And if decision makers cannot understand how artificial intelligence reached a result, hesitation may enter the chain. The new baseline, therefore, requires 3 things at once: better models, better observations, and better translation between science and action. Remove one, and the system weakens. Better models without observations can drift. Better observations without models may not provide enough lead time. Better science without communication may not change behavior. That is the systems lesson. The North Sea's artificial intelligence forecast is not an endpoint. It is a mirror held up to the entire coastal risk system. It shows how much society wants faster prediction. It also shows how much faster prediction depends on slower investments, gauges maintained for decades, records preserved, datums checked, local thresholds mapped, emergency plans practiced, communities informed, and infrastructure adapted before the next surge makes the choice for them. The sea is rising into the space between those actions. That is what makes this moment feel larger than a technical upgrade. A 4-kilometer grid and an hourly forecast can be important. A neural network trained on decades of data can be impressive. But the more important transformation is the one happening outside the model. The old safety margin is being thinned from below. In that world, the question is not whether artificial intelligence can forecast the next surge. The question is whether the whole system can recognize when the past is no longer a safe baseline, and whether it can act before centimeters become consequences. At this point, the story has to slow down and separate the signal from the noise. Because when artificial intelligence, climate change, storm surge, sea level rise, historic floods, and infrastructure risk are placed in the same frame, the temptation is to make every connection sound certain. That would be dramatic. It would also be wrong. A serious warning must not become a loose argument. The first thing that is genuinely connected is the physics of storm surge. Low pressure can raise the sea surface. Strong wind can push water across a shallow basin. Tide can lift the baseline at the wrong hour. Waves can add overtopping risk. Coastline shape can amplify or reduce local impact. These are not speculative claims. They are the physical foundation of storm surge forecasting, and they are the reason the North Sea has always required careful warning systems. The second thing that is genuinely connected is observation. Tide gauges, sea level records, and real-time coastal measurements are not optional decoration around the forecast. They are part of the forecast system's contact with reality. They help evaluate models, correct errors, monitor events as they unfold, and preserve the long-term record needed to understand changing sea levels. Without observations, the system can still calculate, but it cannot know, with the same confidence, whether the calculation is staying close to the sea. The third thing that is genuinely connected is artificial intelligence. Artificial intelligence can matter here. A graph neural network such as Flow can learn spatial relationships across connected parts of the sea and atmosphere. It can reproduce patterns from long records of atmospheric forcing and storm surge behavior. It may help generate forecasts faster, support ensembles, test scenarios, and complement physics-based models. It is not meaningless hype. It is a real technical direction with real promise. But promise is not proof of replacement. That distinction is essential. The Flow study does not prove that artificial intelligence has taken over official North Sea storm surge warning. It does not prove that a neural network is now superior to every physics-based model in operational use. It does not prove that human forecasters are no longer needed. It does not prove that tide gauges have become less important. In fact, the more careful interpretation points in the opposite direction. If artificial intelligence is to become useful in storm surge forecasting, observations become more important, not less. The study itself is careful about this boundary. Flow was trained on historical atmospheric and surge data, and its skill was compared with the numerical hindcast on which it was trained and with water-level observations. But because the training hindcast did not include data assimilation, the model was not expected to systematically outperform the numerical model when compared with observations. That is not a footnote. It is the guardrail around the entire story. It means a machine can learn the modeled sea very well and still require the measured sea to remain honest. The fourth thing that is genuinely connected is sea level rise. A higher mean sea level increases the chance that storm tides will reach damaging thresholds, even if the storm itself is not unprecedented. That is a well-established climate risk mechanism. It does not require every storm to become stronger. It requires the starting line to move upward. When the baseline rises, the same surge can become more consequential. But here, too, precision matters. It is not scientifically responsible to say that one particular North Sea surge, by itself, proves climate change. A single event can be influenced by climate change, local sea level rise, natural variability, storm track, tide timing, and many other factors, but proving the degree of climate influence requires attribution analysis. That kind of analysis compares the likelihood or intensity of an event in the current climate with a counterfactual climate without human-driven warming. Without that analysis, a narrator should not claim more than the evidence allows. So the correct statement is not that this storm surge happened because of climate change. The correct statement is that sea level rise increases coastal flood risk by raising the baseline on which storm surges occur, and that this makes accurate forecasting and observation more important over time. That is less sensational. It is also more serious. Another thing that must be separated is weather from climate. Weather is the specific storm, the pressure system, the wind field, the tide phase, and the local forecast window. Climate is the long-term statistical background that shapes how often certain thresholds are reached and how much margin coastal systems have. A storm surge warning lives in weather time. Coastal adaptation lives in climate time. The two interact, but they are not the same. Confusing them can damage public trust. If every coastal flood is described as a direct climate fingerprint, careful viewers will notice the exaggeration. If climate is ignored entirely, the larger baseline shift disappears. The honest position sits between those errors. Individual events need event-specific evidence. Long-term risk is already being reshaped by sea level rise. The same discipline is needed with artificial intelligence. It would be wrong to describe artificial intelligence as a magic shield. It would also be wrong to dismiss it as irrelevant. A machine learning model can be valuable precisely because storm surge forecasting is a pattern-rich problem. The sea responds to pressure, wind, tide, basin shape, and previous state. Those relationships are complex but not random. Artificial intelligence can help learn them and generate rapid approximations that may be useful within a larger warning chain. But artificial intelligence cannot remove the need for physics. It cannot remove the need for observations. It cannot remove the need for forecaster judgment. It cannot remove uncertainty in the weather forecast that drives the surge forecast. It cannot know the condition of every local drain, pump, barrier, quay, or road unless those details are represented in data. It cannot guarantee that a rare combination outside the training distribution will be handled perfectly. This is the danger of treating a model as evidence by itself. A model output is not the same as a measurement, a forecast is not the same as an observation, a hindcast is not the same as a lived event, a coloured map is not the same as the water level at a harbour. Each one has value, but each one occupies a different place in the evidence chain. When these categories blur, risk communication becomes unstable. A viewer may see a sharp forecast map and assume precision. A decision maker may see hourly updates and assume certainty. A public official may see artificial intelligence and assume superior intelligence in every context. A community may hear that the model is advanced and assume the coast is safer than before. But a system can be technologically advanced and still vulnerable if its observations are sparse, its local thresholds are poorly understood, or its warnings are not acted on. So what is only coincidental? The arrival of artificial intelligence forecasting research does not mean a disaster is imminent. A new model being studied over the North Sea does not mean the region is suddenly unprotected. A discussion of the 1953 flood does not mean the same tragedy is about to repeat. A higher sea level baseline does not mean every storm will produce catastrophe. A single high water event near a port does not automatically prove a basin-wide failure. These distinctions protect the story from becoming cheap fear. They also make the true risk easier to see. The real risk is not that artificial intelligence exists. The real risk is a mismatch between confidence and evidence. Confidence can come from a faster model, a sharper grid, longer training data, smoother visualizations, and the authority of modern computing. Evidence comes from observation, evaluation, verification, uncertainty analysis, and performance during difficult events. When confidence grows faster than evidence, the warning system becomes fragile in a new way. It may appear stronger because its outputs are more sophisticated, while its ability to notice local error remains limited. The real risk is not that the North Sea is unforecastable. The real risk is that some parts of the coast may be more locally complex than regional forecasts suggest. A 4-kilometre grid can represent broad basin behaviour, but flood impacts occur at smaller scales. Water does not enter a town at the scale of a model cell. It enters through openings, low points, drainage networks, estuaries, roads, yards, basements, and infrastructure nodes. A model may be right about the regional surge and still miss the local consequence that matters most. The real risk is not that tide gauges are old technology. The real risk is that old technology becomes invisible because new technology is more exciting. A tide gauge network is easy to take for granted until a storm approaches and every centimetre matters. It requires maintenance, calibration, communications, redundancy, and long-term funding. The most important infrastructure in a forecast system may be the part least visible to the public. If it is neglected, the artificial intelligence layer above it has less truth to hold on to. The real risk is not only water height. The real risk is compound stress. A storm surge may coincide with waves, rainfall, river flow, saturated ground, port operations, power demand, staff shortages, transport disruption, and public warning fatigue. The flood risk is not simply the water level in isolation, it is the interaction between water level and the systems waiting behind the defense line. In a connected society, the first flooded point may not be the most damaging point. The most damaging point may be where the flood interrupts another system. There is also a risk in assuming that better forecasting alone equals adaptation. Forecasting buys time. It does not raise a road, protect a substation, maintain a barrier, move a vulnerable household, restore a salt-damaged railway cabinet, or redesign a drainage system. Better warnings can reduce harm only if institutions, infrastructure, and communities are able to respond. Forecasting is one piece of resilience. It is not the whole structure. This is where the story must resist both despair and comfort. Despair says the sea is rising and nothing can be done. That is false. History shows that warning systems, engineering, preparedness, and public policy can greatly reduce loss of life and damage. The comparison between older North Sea disasters and later defended events proves that systems can learn. Comfort says the system has learned enough. That is also false. Sea level rise, aging infrastructure, growing coastal exposure, and increasingly complex dependencies mean that yesterday's readiness cannot simply be copied forward. The system has to keep learning, and that learning depends on measurements that show how the coast is actually changing. The most honest conclusion is therefore narrower and stronger than alarm. The North Sea's move toward artificial intelligence forecasting is not the problem. It may be part of the solution, but artificial intelligence does not cancel the need for observations. It makes the observing network more central because every advanced forecast must still answer a basic question: is the real sea behaving as predicted? If the answer is yes, confidence grows. If the answer is no, the system needs to know quickly. That is the credible warning. Not that a machine will fail, not that a storm will inevitably become a catastrophe, not that every flood is climate change made visible in a single photograph. The credible warning is that coastal safety depends on an entire chain, and the chain can be weakened when society invests in the most visible links while neglecting the quiet ones. Models are related. Climate is related. Sea level rise is related. Infrastructure is related. Observation is central. What remains uncertain should remain uncertain. What is not yet proven should not be claimed. What is only coincidental should not be turned into causation. But what is real should not be softened. The margin along the coast is thinning, the systems behind the coast are deeply connected, and the forecast of the future will only be as trustworthy as the observations that keep it tied to the water. At the end of this story, the image should return to the beginning. A grey North Sea, a forecast model running hour by hour, a line of coast waiting behind defences, a tide gauge in a harbour, almost invisible, measuring the water as it rises and falls against steel, concrete and stone. It is not a dramatic object. It does not look like the future. It does not glow like a satellite image or move like a forecast animation. It does not have the language of a neural network, a high-resolution grid, or a machine learning breakthrough. It simply records, centimetre by centimetre, hour after hour, storm after storm, year after year. And that is why it matters. The future of storm surge forecasting around the North Sea will not be decided by a choice between artificial intelligence and traditional science, as if one must defeat the other. That is the wrong story. The real future will be decided by whether the newest systems can remain tied to the oldest requirement of warning, contact with reality. A model can be fast, it can be elegant, it can be trained on decades of data. It can learn the shape of a basin, the response of water to wind, the pressure patterns that usually precede danger, and the timing that separates a nervous tide from a flood emergency. It can produce forecasts at speeds that older systems could not easily match. It can help forecasters explore possibilities, run scenarios, and see the basin as a connected system. But the sea is not the model. The sea is the object that must be measured. That is the central message. Not that artificial intelligence is a threat, not that old forecasting is enough, not that the North Sea is doomed. The message is sharper than that. As the forecast becomes more intelligent, the observing network beneath it must become more important, not less. Every advanced prediction still has to answer the simplest question in coastal safety. Where is the water now? That question is almost primitive in its clarity. It cuts through every dashboard, every model layer, every color scale, every probability range, every policy document. Where is the water now? Is it rising faster than expected? Is the peak coming earlier? Is the tide and surge aligning? Is one harbour diverging from the forecast? Is an estuary behaving differently from the model? Is a quiet sensor reporting the first sign that confidence should change? This is why observations are not a supporting detail. They are the hinge between prediction and action. The North Sea has taught this before. It taught it through past floods, through emergency reforms, through tide gauge networks, through barriers and dikes and warning centres built after water exposed the cost of unreadiness. But every generation has to relearn the lesson in its own language. One generation learned it through broken defences, another through numerical models. This generation may have to learn it through artificial intelligence. The language changes. The water does not. Pressure still falls, wind still pushes, tide still rises, waves still overtop, low land still waits behind walls, drainage still fails when the sea outside is too high, salt water still enters places designed for dry conditions, ports still depend on thresholds, railways still depend on exposed corridors, power systems still depend on substations, cables, access roads, and maintenance crews. Families still depend on warnings they can understand in time. That is why the story cannot end at technology. It has to end at the system. A storm surge warning is not one model output, it is a chain. Weather prediction feeds ocean prediction feeds warning centers, tide gauges test the forecast, human forecasters interpret the disagreement between model and measurement, agencies translate that judgment into warnings, local authorities decide what to close, where to send help, which communities need attention first. Infrastructure operators decide whether to keep ports open, stop trains, close barriers, move equipment, or shut down exposed systems. The public decides whether to act. The chain is only as strong as the part that fails under pressure. A brilliant model cannot compensate for a broken sensor if the broken sensor was the only eye on a vulnerable harbor. A fast forecast cannot protect a town if the warning is not understood. A warning cannot protect a care home if no one has a plan to move residents. A flood barrier cannot protect a city if it is not operated at the right time. A tide gauge cannot help if the data do not arrive when the decision is still alive. This is the sober meaning of resilience. It is not one invention, it is coordination. Artificial intelligence may become a powerful part of that coordination. It may help the forecast system move faster. It may help reveal patterns that are difficult to see across a whole basin. It may support ensembles, compare scenarios, detect anomalies, and guide attention to places where the forecast and the observations no longer agree. Used carefully, it could become one more way to buy time before the water reaches the threshold. But time is useful only if it is converted into action. That is the difference between a forecast and protection. A forecast can say the water may rise. Protection means someone knows which street floods first. A forecast can show a regional surge. Protection means the port knows which access road will close. A forecast can update every hour. Protection means the tide gauges are functioning, the operators are watching, the uncertainty is understood, and the warning chain has practiced the moment when action becomes necessary. The North Sea is not only a scientific problem, it is a governance problem, an infrastructure problem, a public trust problem, and a memory problem. It asks whether societies remember why warning systems were built. It asks whether governments fund the quiet equipment before the loud disaster. It asks whether ports and cities know their own thresholds. It asks whether climate adaptation is being treated as a distant planning exercise or as a daily shift in the baseline beneath existing systems. It asks whether the people most exposed are being given enough time, enough clarity, and enough help to act. And above all, it asks whether confidence is being earned. Confidence should not come from the words artificial intelligence. It should not come from a sharper map alone. It should not come from a long training record alone. It should come from performance tested against reality, from observations that confirm or challenge the forecast, from forecasters who understand the limits of the tool, from institutions that can act on uncertainty, and from communities that trust warnings because those warnings have been honest before. That kind of confidence is slower to build than a model. It is also harder to fake. This is why the missing key is so uncomfortable. It is not glamorous. It does not fit easily into a headline about the future. It does not promise that technology will save the coast by itself. It says something more demanding. The future of forecasting depends on the maintenance of truth, on gauges that keep working, on records that keep growing, on reference levels that are checked, on data streams that survive storms, on scientists and agencies willing to say what is known, what is uncertain, and what must be watched more closely. The coast does not need a perfect system. It needs a system that knows when it might be wrong. That may be the most important sentence in the entire story. A dangerous warning system is not one that admits uncertainty. A dangerous warning system is one that hides it. Uncertainty, when measured and communicated, can lead to caution. Hidden uncertainty can lead to false calm. A model that says there is a range of possible outcomes may be frustrating, but it is honest. A system that presents a single clean number, while the gauges are beginning to disagree, is more frightening. The North Sea's future will be lived inside those disagreements. Between model and measurement, between historical design and rising baseline, between regional forecast and local flood point, between public expectation and physical margin, between the speed of computation and the slowness of infrastructure adaptation, Sea level rise makes each disagreement more consequential. When the baseline is lower, there is more room for small errors to be absorbed. When the baseline rises, the margin shrinks. A few centimeters become less like rounding error and more like the remaining space before overtopping. A 1-hour timing error becomes less like a forecast inconvenience and more like the difference between high water passing safely and high water arriving with force. A local blind spot becomes less tolerable when the systems behind it are dense, connected, and expensive to repair. That is the future beginning to take shape. Not a future where every storm becomes a catastrophe. Not a future where artificial intelligence fails by definition. Not a future where nothing can be done. A future where the cost of being slightly wrong is higher than it used to be. That is why the story should leave the viewer with tension, not despair. The North Sea has learned before. Societies around it have built defenses, warning systems, tide gauge networks, forecasting services, emergency plans, and engineering works that have reduced risk and saved lives. Human beings are not helpless in front of water. Science matters. Infrastructure matters. Public policy matters. Preparation matters. But learning is not something a system does once. It has to keep learning. It has to learn from near misses, not only disasters. It has to learn from gauges, not only models. It has to learn from small floods, not only historic ones. It has to learn from communities, not only agencies. It has to learn from the places where the forecast was almost right, but not right enough. It has to learn from the quiet evidence that the old baseline is no longer holding. That is where artificial intelligence could become valuable if it is used with humility. It could help process more information than human teams can easily handle. It could help reveal patterns across the basin. It could help compare possible storm evolutions before a single deterministic forecast becomes too seductive. It could help identify places where observation and prediction diverge. It could help make the warning system faster. But humility means remembering that speed is not truth. Truth still has to be measured. A tide gauge in a harbour may seem small compared with an artificial intelligence model trained on decades of data, but in the moment of decision, the small thing may carry the decisive fact. The model may describe the basin, the gauge describes the contact point. The model may show what should happen, the gauge shows what is happening. The model may extend sight into the next hours. The gauge keeps the present from becoming imaginary. That is the relationship the future requires. Not model over observation. Not observation without model. Both bound together, each correcting the other. The North Sea will continue to be a place of wind, tide, trade, energy, memory, and risk. Ships will move through it, turbines will stand in it, cables will cross it, ports will depend on it, towns will face it, barriers will hold against it, scientists will model it, gauges will measure it, and storms will continue to test whether all those human systems can remain aligned when the sea stops behaving like background scenery and becomes an active force. The event that opened this story will pass into another file, another study, another operational lesson, another piece of the long record. The model will be refined, the data will be evaluated, the next forecast will come, the next storm will form somewhere over the Atlantic or the northern seas. Pressure will fall, wind will turn, water will move, tide will rise. And again, the question will return. Not only what does the model say, but what does the sea say? That question is the reason the observing network cannot be treated as yesterday's technology. It is the reason a tide gauge can be as important as a neural network. It is the reason a centimeter can matter as much as a headline. It is the reason the future of coastal safety will depend not only on smarter prediction, but on the stubborn, physical act of looking. The North Sea's storm surge forecasting may be going artificial intelligence, but the coast still needs eyes. And as the baseline rises, as the margins thin, as ports, power systems, roads, homes, and flood defenses become more tightly connected to every forecast, the question left behind is not whether the next model will be faster. It is whether the world beneath that model will be observed well enough for anyone to trust what speed is telling them.